and this is Balls Out Physics, Episode 1, Planes Flying on a Spinning Ball. About 7 months ago, or well, 8 months ago, beginning of the year on New Year's Day, I went and saw Interstellar, and I thought it was awesome. And it got me to go back and read this book for probably about the third time in my life, What is Relativity? It was written in 1959. Really good book, very good explanation of relative motion. From planes moving across the earth with balls bouncing inside them all the way up to things traveling at the speed of light. It gives a really good explanation of Einstein's theories. And so, here I am, my head in the clouds, thinking about relativity and space travel and all this craziness. And I was, just bored one day, sitting on the couch, looking through YouTube videos, and a couple flat Earth conspiracy videos popped up in the, that suggested videos to watch. And I'd seen those before, and I always had thought to myself, there's just no way, But I'm a very open-minded person, and I was, in the mood to watch something different. So I said, what the heck, I'll watch one of these, thinking it would be good for a laugh. Well, about halfway into it, I wasn't really laughing. I was actually questioning a lot of things. And one of the biggest things that caught my attention was planes flying on a spinning Earth, trying to land on north and south runways. Because the Earth rotates from west to east, and things don't seem to line up based on the examples they were showing. This was all graphically, and so I started to look into this a lot. And what really surprised me at first is, I'm a structural engineer, and I've taken a lot of physics courses in my life, and I started to look into the curvature of the Earth and the rotation and the speeds of Earth, and it kind of blew my mind that I'd never really thought about how fast the Earth rotates or how much it actually curves. Here I am researching flat Earth theory, and I'm actually studying the curvature of Earth and the speed at which it rotates. I mean, there's some serious irony there. Our Earth, our model shows it spinning from west to east around an axis, which is represented by this little stick, and the circumference of the Earth at the equator, right here, is, the circumference of the Earth is 24,901 miles. So at the equator, since that's the farthest point from the axis of rotation, and there are 24 hours in a day, the speed of the Earth is 24,901 miles divided by 24 hours gives you 1,038 miles per hour. That's the instantaneous velocity at any point along the equator. I mean, that's what it has to be if everything we're told is true. So that's really fast. That's faster than the speed of sound, which is Mach 1, 761 miles per hour. So I never really thought about how fast that is. I always thought just kind of assumed it was moving really slow, and you don't really think about how much distance has to be covered in one day. But I also had never thought about or even calculated how much it actually curves. The general accepted value is 8 inches per mile, and I mean that's what it has to be based on the circumference, and that's 8 inches per mile varying with the distance squared, because if you're standing, or if you're on a point that's just above the surface of the Earth, or just on the surface of the Earth, and you look straight out away from you across water, of course, because land has mountains and all kinds of things, but going across the surface of water, at the first mile you would expect to see an 8-inch drop down to the curve, and at the second mile, because it's a curve curving down, it's continuously getting farther away from that horizontal line that you're driving, that you're sighting out away. The second mile is 8 inches times 2 miles squared, which is 32 inches. And then the third mile is 8 inches times 3 miles squared, and if 3 miles squared is 9, it gives you 72 inches. It starts to drop off pretty quick. And so I'd found that the flat Earth community had created this. Someone out there did this. This is a curvature chart. The flat Earthers are making a curvature chart, and they're showing how much curvature would have to be, we would have to see in all directions, because it's a sphere, anywhere on Earth. And this was drawn in AutoCAD, and since I'm an engineer, I have access to AutoCAD. The first thing I did is I went and drew a circle with a radius of 3,959 miles, which is the accepted radius of our Earth. I converted that to feet, which comes out to over 20 million feet, and started plotting points and finding that this is very accurate. This is exactly what you get. So I'm starting to wrap my head around how much curvature there should be, and that's quite a bit. And it's kind of hard to find it. So anyway, one of the first things I did is I set up a problem about the spinning planes. It was a physics problem. I'd studied relativity. I figured I could do this. The idea of this problem is that we are an observer, a stationary observer, looking at Earth, watching a plane fly. And this is based on a direct flight I took in college from JAX to LAX. The two airports are about 2,000 miles away from each other. And I flew there and then flew back, and I like doing the problem going back because it's more interesting that way. Because we're rotating with the Earth, and also a lot of some flat earthers out there have said things like, if the Earth is rotating 1,000 miles per hour at the equator, planes can't fly that fast, so they can't catch up to it, and that's not really true, because if the plane's already rotating with the Earth when it takes off, the speed it gains in the air is added to the initial speed it already had. So that's not true. But there is a problem here, and that's what I want to get into. So these two airports are 2,000, here's my dimension line here. They're 2,000 miles apart roughly. We're just going to say they're 2,000 miles apart in order to keep this simple. Okay? And they're also, they're not at the equator. They're north of the equator. A little over 2,000 miles, both of them. Jacksonville's over here in Florida, and LAX is over here, California. LAX is about 250 miles north. I think 250 miles north of JAX in Jacksonville. But we're going to say that they're at the same latitude, just to keep it easy, to keep the problem easy. And so, as I was showing you on the ball, as you move up away from the equator, the diameter of the Earth around the center axis decreases, so your velocity decreases. You can calculate this, and I played around with some numbers, and I got between 850 and 900 miles an hour for both airports. So I just said let's just use 900, just to keep it easy. It's a hypothetical problem, but it is based on reality. So the reality we're all taught to believe. So here we are. We're going to fly back to JAX. Sitting on the airport in LAX, we're going 900 miles an hour east. The Earth is moving that fast, but we can't feel it because everything's stuck to it, right? So we're told. So the plane takes off and gets up to its cruising altitude, whatever that is for the day, 30,000, 33,000 feet, whatever they're going to fly at. And it gets up to a cruising speed of, let's say, the velocity of the plane, VP, equals 600 miles per hour. Now, since it was already moving, the velocity of the plane relative to Earth, which we'll call VPE, is now 600 plus 900 miles an hour gives us 1,500 miles per hour. This thing's really moving. Okay, but it's relative velocity, so it only seems like 600 miles per hour to us on the plane, right? That's the theory. So everything makes sense. We're moving fast, 600 miles per hour faster than the Earth is spinning, so we're moving towards Jacksonville. But here's where we run into a problem. Let's say there's a north-south runway in Jacksonville. Now, Jacksonville's runways are actually orientated kind of 45 degrees northwest and northeast, but north-south runways do exist. You can go look on Google Earth, you'll find them. They're all over the place. And of course, LAX's runways all point east-west. I mean, they're right on the water, or right on the ocean. So we get up here to this point. Right before they make the turn, the plane slows down. Okay, this is where the problem comes in. Planes cannot stop flying before they make a turn. They can't go to zero, and going to zero would bring you back to 900 miles per hour that you started at. But you can't go to zero because a plane has to keep flying forward to have uplift on the wings and keep itself in the air. Duh. So it's going to slow down before it makes the turn, but it's not going to zero. So let's say it slows down to 300 miles per hour. You know, and then it also that's the speed it slows down to before it makes this 90-degree turn, or this right angle turn. So here, the plane, right before it makes the turn, is traveling at VP prime equals 300 miles per hour. And VP prime is just the new speed, okay, or the new velocity in this direction. But it's also got its relative velocity to Earth, which would be VPE prime, is now 300 from 1500 is 1200 miles per hour. So now, as this plane goes through the turn, when it gets here, say the midpoint of the turn, it's got a vector of 300 miles per hour, which is its airspeed, this VP prime in this direction, but it also still has this velocity of VPE prime right up here, 1200 miles per hour. It doesn't lose that velocity. It can't, because the Earth is spinning under it, you know, and it had that initial speed when it took off. The only way you can get rid of that is if you make the Earth stop spinning. So, you know, when you get down here and you're trying to line up with the runway, you're going 300 miles per hour towards it. Make that look a little better. You know, you still got VP prime here, but you also have VPE prime. Well, there's a real problem there, because the airport, the ground over here, is moving, you can see that, at 900 miles per hour. You know, except the velocity of the Earth is the same at both airports. But the plane is moving to the east still at 1200 miles per hour. The plane is moving faster than the runway. They can't line up. What you actually get, if you draw this point over here, actually let's erase this and do it right here where we started. What you would actually end up with is a path that looks like this. More of a linear path, because the plane, you know, if this point represents the plane has a vector this way and another much larger vector this way. So you're getting something like that. The plane is actually sliding sideways through the air. That doesn't make sense. I mean, it's kind of what's going on. You know, this question, of course, people say, well, the atmosphere, this is what I thought too initially, the atmosphere is moving with the Earth. So, you know, since the atmosphere is moving with the Earth, you know, it's like a fluid that you're traveling through, so it doesn't matter that your initial speed was 900 miles per hour, and then you have a relative speed, and that doesn't work. When you really start to think about it, it doesn't work. You know, the best example I got from another engineer I showed this problem to was, he said, what about a fly on a train? You know, the train, the air in the train is moving with the train, and the fly can buzz all around inside the train. You know, you've probably seen bugs in a vehicle before of some sort. You know, and the fly is unaffected by the movement of the train. Well, first of all, a fly can hover, which a plane can't do, and also the air in the train is contained within the shell of the train. Earth does not have a shell that, at least so we're told, that contains all the air. You know, the space shuttles and rockets and everything flies through it. You know, they leave the Earth. What's supposed to hold our atmosphere to our Earth is gravity. So we're told, you know, air actually still has a mass, and so gravity pulls. You know, anything with mass exerts, as we're told, anything with mass exerts a force on anything else with mass, and they attract each other. I'll get into that in another episode, because that's also a big issue I'm finding. But so the atmosphere, you know, spinning with the Earth, you know, wind blows in all different directions. It's not constantly blowing from west to east, because if it was moving with the Earth, it would be blowing from west to east, and that wouldn't help us at all, because, you know, the plane is also going from west to east. So if anything, the atmosphere is just pushing it along. It's not helping slow it down. If you reverse the problem and go the other way and flip the runways around, which is what I initially did, you end up with the plane going 300 miles per hour too slow. And of course,